Hi, everybody. Welcome to our talks today. We're going to have three talks today from some of our gap year students. First up is Andrii. Andrii, whenever you want to get started, go right ahead.
Right? Yeah, I will start now. Can you hear me well?
Yeah.
Okay. Yeah, so hi everyone. I'm Andrii Povsten, and I would like to share with you my experience working as a gap year student in IRIS-HEP here at CERN. So my project is Analysis Grand Challenge on REANA, and I was doing it together with Alex Head, Matthew Fiker, Oksana Shidura, and Tibor Shimko. So let's just start from the fundamentals. So the Analysis Grand Challenge is the analysis which is made to process to extract the columnar data from the large data sets, then it processes this data by event filtering, like the evaluation of systematics and circumstances into the histograms, then applies some sorts of statistical model construction and statistical inference with proper relevant visualization. Here you can see typical pipeline with the data access, the event selection, histograms applying using all sorts of the HEP analysis software, and then creating the workspace. So my initial objective was to add the analysis preservation step to this AGC pipeline. So for this, I was using the REANA, which is a reusable analysis platform, which allows physicists to submit the complex like physics analysis and then them to be executed like in a single command. It uses container technologies such as the Docker Singularity, compute clouds like Kubernetes, OpenShift, with shared storage systems, EOS and Ceph. And here you can see typical UI interface of the REANA and the REANA architecture. All right, so hopefully everybody's like on the same page now. Right, so initially our analysis grand challenge runs on the Cppyy, and it would process the more than 700 files, which is related to the 9 samples, and then gives us the proper output. So in order to make our analysis more reusable friendly, we kind of need to change the structure and like start from the fundamental syntax piece. So what we was thinking about is to process not the whole 700 plus files at once, but process like rather one file and then make in parallel. So processing 700 files in parallel and then make merging steps. So to adapt this, we were using the snake-make workload management system, which the main syntax is to have rules which would run as separate jobs. So we created a rule which would take our AGC original analysis and we just run one exact file. And since it's nicely integrated into the REANA would take this snake-make rule and then take it into the pod and submit this pod directly into Node where it will be processed. So this technique, it's called like multi-cascading approach. So initially we had the 700 files, which would take as a job, as a rule, as a job, that would process in parallel. And then after this, when everything is processed, then we would merge it firstly per sample and then everything together and have the loss and other statistics. Right, so the achieved results which we have for processing, merging all the files, and then the creating of the final workspace JSON, which was made with Cabinetry tool package, it takes around like 6-7 minutes with REANA. Here you can see the report which is generated by snake-make automatically after the workflow is finished. Here we basically just have the one rule which would repeat it 700 times and execute it in parallel at the same time, more or less the same time. 700 times, and then we have the process which is merging for sample, and then the final process merging. Sorry. Right, and during our tests, we also made some sort of the benchmarking experiments, like our trials and errors. Here you can see them. We made some kind of benchmarking, and one of them, which is pretty useful, is the lifetime of the pods, which means like lifetime of the jobs, where you can see the creation, pending, and the finishing of the pods. So basically, you can estimate how much how many jobs were running exactly in parallel, how many were waiting, and so on. And also, we made figures which would show the total CPU and memory usage per timestamp, which is also useful in terms of, okay, if we understand how many memory are using at this specific time, so we can decrease the Kubernetes memory limit per job, and which allows to REANA then to submit more jobs in one single node, which is then eventually will increase the execution, the whole execution time, or decrease the whole execution time. Right. So eventually, after making, so these benchmarks were and the discussion, these benchmarks was really useful for REANA team in terms of improving the REANA performance. So here just few of them, which is worth mentioning, like the general SnakeMake engine version upgrade. And here, hope you can see the cached improved mechanism example. So initially, the REANA job controller would check each time if the file which we needed later already in the workflow already existed. So it can be cached and used later. So it would take some time. But it turns out that SnakeMake automatically is doing it. So this mechanism was rudimental, and it got rid of it. And then eventually, the workflow would take less time for checking if the file already exists because it's done by SnakeMake. Also, yeah, we avoidance of the EOS input files throttling by using authenticated user. And one more thing which was improved and which you can really see on the benchmarking figure is the faster terminating of the jobs by improving the refresh token sidecar termination. So basically the job would finish much faster, and then the start of the new job also will start much faster. All right, so after we did the reusability, we make our analysis more reusable, we ask ourselves, okay, where we can install, where we can put our data, and that we can be used later. So for this, the HEP data was a perfect fit. Basically, just the open access repository that the physicists can upload their results, and then it can be you can make some you can see some analysis and some histograms even like in the UI interface. It was made and maintained by the Durham University. So the general approach, how can you submit your results to the HEP data, is just by simply installing the HEP data lib package. Then you just fill in the submission object and then it will generate the necessary folder. You just add some required description, which you can understand later what was this analysis about, and create a zip archive. And then you can have like two options. Just by installing the HEP data client, you can directly like submit while running, for instance, on REANA, your workflow, it would directly submit it to the HEP data, or you can just download files locally and then submit it via sandbox. Here's kind of the UI interface. It's one of the output histograms which made by AGC in REANA run. Here you can see. Yeah. So, and then after this, we also ask ourselves, okay, what if we have the additional sample, which we don't want to, like, not to use much computational resources, not to run everything again from the scratch with all previous samples which we also needed. So for this, we kind of get up with recast, I would say philosophy recast approach, which means like try to change the initial parameters and then just try to have some new background. So okay, we have our current AGC workflow, which is like with all changes for reproducibility, and which process the root files, and then you can just submit them directly, as I discussed, to hepdata, or just you can use REANA directly. If you will use it REANA later, you can just submit it. You can just download it, sorry, from the previous REANA workspace to a new one by using the REANA client tools. So what we did, we just basically took our workflow, which was a nice thing because we didn't change much things. We just took our reproducible AGC and just changed the input data with new sample and then process it again. And in the end, we received a new workspace with a new sample. And after this, we download these workspaces together. We download these both workspaces to the hepdata from the hepdata, and then just by simply applying the Python JSON patch library, we're able to create a new patch. And thanks to the PyHEP developers, which allows you to easily manipulate your patches, we just applied the created patch to the old workspace, which was generated some time ago. And then we received the new output histogram, something like this, if you can see. And yeah, and the last but not least, what I want to mention, which was tested, is this AGC and service export. So basically, all our files were located at the EOS public instance. But imagine if your files like located somewhere else. Like in our case, some of the files are located or were located on the UNL instance. So we used the service X, which is data delivery service. It was already integrated to the original AGC. And the thing about it, it's just allows us to use the files which are cached with service X, which would decrease the time execution. So we again just used our already reproducible changed the AGC workflow, then gave the service X files which is stored in mini object store. In our case, it was in UNL mini object store, but you can have your own locally. And then, yeah, the service X, the data delivery first, it took like more than 1,000 seconds, but eventually you have your files, which is from UNL, not located on the EOS, which is much less by size, but therefore they're processing much, much faster, like few seconds, basically. Right, and yeah, in the conclusion, we successfully implement the AGC pipeline in REANA, just throw multi-cascading snakemake, run many benchmarking experiments, like test the service X, like implement the submission of the workflow results to hepdata, and the cast like multi-workflow AGC was implemented. One of further work would be to benchmark AGC pipeline with task on REANA, which is a current project by the technical student in the REANA team, and this further testing of service X for AGC in REANA. Yeah, that's kind of it, what I want to say. If you have any questions.
Thank you, Andrii. Any questions for Andrii?
No, maybe just a comment from his supervisors. and to thank for this amazing job that you did over the last year. Also, it was interesting because this project allows us all to work more closer to REANA team. So I think it was wonderful job. Thank you a lot for doing this for us. And I hope you will have a very nice, bright future ahead of you.
Yeah, I can only echo that, and it was also a great opportunity for me to learn more about some of the things you ended up using, because you're sort of bridging the gap between, for example, AGC and REANA. So it's a good opportunity for me also to learn more about that side of the things. I appreciate that. Thanks.
Yeah, and maybe one comment also from my end. I really also enjoyed a lot the collaboration. Alex, Oksana, thanks to your work, Andrii, we have identified a lot of places in REANA where we could optimize things. So it shows how AGC is useful for, let's say, analysis facilities to be ready for like a large workflows. And we already have like things to do in the future, such as Dask and ServiceX. So the collaboration was very nice. I enjoyed it a lot, and it opened doors for more to come.
All right, so that sounds like it was a great experience for everyone. So thank you again, Andrii. Up next, we have Zoe. Zoe, if you want to go ahead and share your screen.
Can you see
Yeah.
everything? Okay. So this year I worked on multiple projects, but related to Columnar File I with hepconvert and Uproot, and I worked under Jim's supervision. So as I said, my two main projects were creating the Python package hepconvert for columnar conversion in Python, and while working on this project, I became familiar with Uproot and root files, which served as a good precursor to a more in-depth project with Uproot. So after working on hepconvert, I worked on a new feature for Uproot, adding new T branches to an existing T tree. So first I'll introduce hepconvert. It's a package to address unnecessary time spent between physicists converting between different columnar file types. There's no easy way to do this without hepconvert. You have to use multiple IO packages, write multiple lines of codes, and to alter this process in any way, users have to write additional code and just be familiar with multiple IO packages. And many users are writing very similar code, which is good cause for a new tool. So it's a Python package that uses existing IO packages such as Uproot, Awkward, to convert between common file types, root and Parquet. So the goal is convenience, so quick, simple file conversions with just one function call, so it'll be easy for physicists to remember and not require them to think about how to what functions to use for each conversion, and they don't have to think about memory management or functions for setting compression. And there are additional customizations that allow users to alter files and alter data without writing additional code. So I'll do a quick overview of the features I implemented. So converters between root and Parquet, root to root, including merging functions, HAdd, and a root copy function. And most of these converters have file manipulations included as parameters, so users can add and remove data quickly, change compression settings, and there's also a command line interface. So all of these functions allow users to easily read and write in batches. It's automatic if files are large enough, and it's also easy for users to customize. And for new users who aren't super familiar with data types, I mean, with these different file types, they don't have to learn about like how to go between two different file types if it's confusing. For example, root files have entries, whereas Parquet files have row groups, but these don't mean the same things. And normally you might have to think about how to deal with this. So yeah, that's included in each function call without users having to write a for loop or anything. So work with root files. Users don't need to have root installed to use this package. It's pure Python, which is an advantage. It uses Uproot, so therefore it has the writing capabilities and also limitations of Uproot. So it works with flat T trees and NanoAD like files best. More specific information is in Uproot's documentation. So one feature is going from Parquet to root and the function, Parquet to root. So the way hepconvert handles these types is one whole Parquet file will become one T tree. I have implemented merge Parquet, so users could theoretically merge multiple Parquet files together and then convert that to one tree if they have multiple files, but they only want one T tree in a root file. And this has the writing capabilities of awkward array, so there are lots of like different features usually when reading Parquet files. So yeah, and same with root to Parquet. So one T tree becomes one Parquet file. And again, if you want multiple T trees to become one Parquet file, you could first merge the T trees. hepconvert has a function for that too. But otherwise, one T tree will become one Parquet file. Yeah, or you can specify one T tree from a root file to write. For the step size, if you are writing in batches, you specify the step size that will become the row group size of the new Parquet file. And for this, users can do branch skimming or branch slimming, so selecting data in different ways as a parameter. And wildcarding and regular expressions are accepted for how you select your data. So that's pretty easy. I also implemented a feature for awkward array, or re-implemented. It was in previous versions of awkward array, which is awkward to Parquet row groups. There previously wasn't a iterative function for going from an awkward array to a Parquet file. So to allow users in hepconvert to go from root to Parquet files in batches, I wrote this function, which will essentially read and write. So there's only one row group in memory at a time, so users can write large files. So you pass an iterator instead of a whole array. I also wrote a function for copying root files. This one is useful because it has a number of features, same as Parquet to root. There's branch slimming. You can also remove T trees and branches. And another bonus from this function is that it avoids Uproot's duplicate counter issue automatically, instead of users having to manually choose and group branches with awk.zip. Yeah, and again, the usual, you can change compression types and it automatically runs in batches, and you can run it from the command line. So another reason why this function exists. So, merging t-trees and histogram summing. So functions like roots HAD. A number of users requested this. And it's nice that you don't have to have root installed, but you can still run these from the command line. I think that's a reason why people ask for it. So at histograms, I didn't want to call it HAD because they're not the same. So it sums contents of histograms in many files and writes us to a new file. And merges t-trees that have the similar structure into one file and some histograms as well. And as usual, you can remove branches or skim branches while you're running this function. So if you want to merge just portions of t-trees and write it to a new file, you can do that easily. So the second project I worked on was adding branches to an existing t-tree. This is a function that exists in root, and there was also some specific use case that users wanted this for that they talked to me about for hepconvert. So this is the goal, to have uproot, add branches, and you have your original tree. And then this is the additional data. So you can add multiple branches with data from a function call. So yeah, here's the specific example. Someone asked, or that initially started this project. So there's a common issue with CMS data. So users wanted to merge nano-AID files, but a lot of them have mismatched branches. So these are two separate trees, but these two branches are different, but they want both of them in the final file. So there's a way that users can, or you can add a branch of just booleans and and before you merge them to allow the files to be merged, but with the data correctly. Yeah, so copying the t-tree and the old branches. So the challenge with this was robustness. We wanted to it not to matter what kind of what branch types are, because obviously having a different case for each potential type of branch would be really difficult. So I tried a few different methods, but what I ended up doing was rewriting the t-tree metadata, serializing it like Uproot normally would, with the correct number of new branches, and etc. But copying branches from the original t-tree directly, like copying the bytes themselves. So yeah, this is the part, that's really serialized, but the rest of it is directly copied, aside from reference numbers, which I update. So yeah, again, this is what's rewritten, but the data directly copied is the entirety of t-tree branches, including t-leaves and t-baskets. So this is done using Uproot's reading ability, as you can use a cursor to identify objects, and you can jump through. So I was able to find the beginning of a t array of t branches, and then find and easily change reference numbers. Yeah, so the beginning of the t-tree is the t-tree metadata and all the old branches. And there's one challenge, or one main challenge with this for me, which was changing t-tree metadata size. So all uproot t-trees have the same t-tree metadata size. There's two, and uproot writes the larger one, but some files written with root have smaller t-tree metadata. But I wanted the new trees to all have the larger t-tree metadata, but this shifts the rest of the file down. So I had to find and update all the TREFs that tell Uproot what kind of object it's looking at. So to find this problem and find all the places where TREFs change was a bit difficult. So that was one main challenge. And adding new branches. So these are appended to the end of the T tree and shouldn't affect the data that was already written and copied. It can only add version 13 T branches, which means that the only kind of T branches that can be copied are version 13, and that the version of T tree has to be version 20, which are all the newest versions by like 7 years. So it shouldn't be a huge problem, as Uproot can only write version 13, which is reasonable. So these are serialized and written very similarly to when a new T tree is written by Uproot, and multiple can be added at once. So yeah, that's a summary of my work this year. Thank you.
Thank you, Zoe. Any questions for Zoe? All right, no questions? All right. Thanks again. Next up is Aaron.
Yeah. I'm just going to share my screen. This is it. Yeah. Am I audible?
Yeah, we can see your screen. Go ahead and get started.
Yeah. Hi, everyone. So I'm going to present how my internship went with IRIS-HEP here at CERN. So over the last 6 months, I was primarily working on CppInterOp, which is a novel interpreter infrastructure providing library, which is or provides a C API to Clang, which lets you plug into LLVM in a much safer and much better way. One of the main aims of this was to plug in to the CppInterOp tool that powers Pyroot, which is one of the best Python C++ language interoperability tools out there. So yeah, I'm just going to get started with a again brief intro back into the tools that I worked on. So CppInterOp, as most of you have used like through Pyroot, it's a runtime bindings generator which gives the user with lets you use a C++ feature set through Python without having to statically bind it as you would with like Cython or PyBind. It uses Cling, which provides you the runtime-ness of the C++ side. And then Clang REPL is a generalization of Cling in LLVM worked on by Vasil, who was my supervisor, that lets you support interactive programming in a REPL manner, which is like a read, evaluate, print loop style. Clang REPL lives inside the LLVM monorepo, which lets us build our tool directly using LLVM. So this is like a quick rundown on the architecture involved. From the Python, starting from the Python interpreter that accesses your front-end pip installable packages, and then you have a proxy that lets you construct these bindings with your interpreter, which is exposed through Cling wrapper, and then you have these interfaces that expose Clang REPL functionality, like get scope, for example, when you want to look up a scope of a function or a data member. So this lets you avoid string parsing logic and then opens up a lot more C++ features and a lot lower dependencies. So yeah, and this is kind of what it looks like. So the unit test layer lets you verify the API. and a huge part of the work involved while trying to fix CppInterOp to work with InterOp is to add more unit tests to the interfaces that you create or upgrade in order to get a coverage of the C++ standard that you're trying to support. And the main advantage here is the fact that you have a much more modular design with a less string manipulation involved. And also, yeah, this is just an example of how that happens. You can see that your interface gets simplified a lot when you have a API on the LLVM side, or that interacts with LLVM. You lose a lot of this groot meta stuff that used to exist in Cling in CppInterOp, and then you work directly with the pointers which are memory safe with LLVM, and let you obtain the declarations that you need. So yeah, this is a unit test that I just put in the slide as an example. This is an older one. There were some new ones that were added throughout the course of my internship. So one of the things I worked on was template support, because template support is pretty important when it comes to how it works Pythonically, and also a lot of the tests that depend on template functions. And a lot of the user code also uses template functions. So this is kind of one of the examples that we aim to support and were able to successfully support at the end of the project, which was being able to do the right kind of type translation, the right kind of selection based on function parameters, even when you have implicit or explicit like instantiations. So yeah, this is like a high-level interface that you would design, and that we designed in Cling wrapper that assists the CppInterOp package with performing the overload selection. So we basically strip out these parameters and then create like a struct that is passed as a vector of these template arg information that, as you can see, has the CPP namespace, which means it's completely managed by CppInterOp, and it's not it's a much better approach than just passing strings. You can get a list of templated methods, which is the interface that says get class templated methods. And then you can use that to try different kind of instantiations and then find the best template function match. Then you also have an interop level interface, which is the lower interface. So this exposes the Clang API. As you can see here, you have like the Clang template parameter list. So we're using like pure Clang to kind of work with what is the best kind of function to call from like the Pythonic level all the way to the compiler level. This gives you a memory address, which is basically a type def void pointer, which is the best suited template function. This selection logic is designed to consider the rules of overload resolution as you would in the C++ standard. The only thing that is kind of like future work is that you can extend this to work with like variadics or specialized templates, although you might need like a cache to deal with some of them if they were pre-instantiated. But yeah, and then this is an interface that provides like on-demand template instantiation using a declaration pointer. So again, this is an interface that works directly with the Clang API. So yeah, this was kind of just one example of the things that I worked on while fixing. So these are like some of the APIs that were bumped up in InterOp to work with the CppInterOp engine. And then at the end of it, you have a lot more added features. So these are features that worked previously with Cling. Well, it's the Cling that lives inside CppInterOp, which was forked from root like a while ago. This kind of makes it work directly with live repositories that are not like forked in the past and then patched. So you can kind of configure interop to work with two different interpreters of your choice. You can choose Clang REPL or you can choose Cling that comes from root. And then all of the results here are these ones are specific to Clang REPL, and then Cling has just plus 10 tests, which are a result of Cling being able to support value printing, and then Clang REPL does not currently support value printing. So 6 of those 10 tests fail because you can't print anything in Clang REPL yet. There's like a PR that's very close to landing that will support it. But coming to how the test suite was revamped through the course of my internship, we have near 200% feature support for Python C++ cross inheritance, which you can see here. There's like an example of importing like a C++ class, like T base one, T derived one, and the other one. And then you can inherit this directly onto a Python class, and then you can, call functions. You can even use template parameter constructors, as you can see in the constructor that we pass int through the square brackets, and that's like a explicit instantiation of the constructor. So this is like an example of something that didn't used to work and then was fixed through a combination of bug fixes. One of them was like the template example. There were others, but I could not like put all of them in the presentation. So there was fixes in this dispatcher mechanism that lets you do the cross inheritance. So that we had 10 tests plus 10 tests passing there. Overload selection tests are near completion, which means there's only like a few edge cases where the overloads aren't selected right. We also have Pythonify, which is almost at 100%. Concurrency, which is more complicated because these are tests that run concurrent, concurrent processes, and then the whole GIL thing comes into picture. And then we have conversions like vector array conversions and basic conversions that give you a Pythonic behavior with C++ entities, which is also almost passing. We have like 100% tests passing for the API, which is the Cppyy API that lets you that basically lets you if you want to extend Cppyy to work on something, you use their API, which is a API on the higher level, not on the Clang level, but nevertheless. We also have the leak checks. So this is pretty important because memory management is complicated when you work with objects that are dealt with by two interpreters at the same time with different language constructs. So the leak check tests were pretty hairy in the beginning, and then as some of the interfaces were fixed, you have improved memory management, and as a result, the tests started to pass. And then towards the end, we had all of the tests passing. Note that this is not completely platform independent yet. There are some issues when you go to like x86 OS X, or some of them that happen on ARM chips of Apple silicon, but yeah, I will go into that. There are some other specific features enabled, like standard basic support in the converters. This one was specifically important because with Clang REPL, you don't no longer have implicit standard strings, where everything is just like goes lower to a standard basic string. So Cppyy had a lot of trouble dealing with these standard basic strings, and then these interfaces were improved to support it. And also enabled a lot of tests. Class loading, template bindings, which isn't here. R value templates, which is just reference type, like template bindings. You have standard pair initialization. And then after standard pair initialization was fixed, I worked on fixing like standard vectors constructor initialization from a standard pair, which you can see. I've pasted an example here, which is a usage of standard vector, standard pair, which lets you Pythonically do that with the lists. And then that goes into your C++ vector, and now you can call like a dot. I mean, you can extend your class pair vector to do anything with C++ vectors, and then you can call them from the Python side, which I haven't done here, but that's the use case. And also built-in casts, which you can see on the top. CppInterOp has a low-level interface called CppInterOp.ll. And then you can use the low-level interface to do casts. So these casts didn't work for built-in types when I started to work on the project, and it turns out that a big reason why this doesn't work is because the way that the type system changed with ClangREPL, there were a lot of interfaces that broke down, and some of them that basically did not exist. So that was also fixed, and then you have like tests like this that started to pass. And then, yeah, so the few other things that kind of improved the test suite was the interpreter. So we had a bug where you needed to forward declare an input to register in the JIT, and previously that wasn't happening. There was that's a typo. Yeah, there were more APIs for CppInterOp support with ClangREPL. There was, like I previously mentioned, basic template function and method support. And then as a result of this, sometimes, bonus tests start to pass, which was libboost and eigen. Although I think libboost is at 3 out of 5 tests, and then eigen has only 1 test passing, but it's a start. So yeah, I just thought I'd put down some stats because I couldn't go through a lot of the in-depth technical details, but cross inheritance had a huge amount of increase in the test passing because the dispatcher that would do it was basically broken. We also have a lot more tests and data types and the doc features, which is also important because one of the good metrics of whether you can support like a general use case is the doc features. A lot of the test suite is designed to kind of stress test cases. Like you have these, like you have a Lambda that's going into like a copy construct. Like, there are cases which are basically stress tests, but you need to ensure that the doc features are passing because they kind of cover the elementary support that CppInterOp has. And although it's not all the way, it has improved since what it was at previously, which was 29 to 40. And eigen, we have one ray of sunshine. That's the one test which initializes a matrix. So now the dependency on eigen is really the heavily templated nature of eigen classes. And then you also have like the fragile tests, which went up by 1. So the API and leak check, like I previously mentioned, are at 100%. So you have all of them passing. And then the CppInterOp.low level interface also went up. So just like from a net standpoint of the impact in terms of what CppInterOp supported, so the status on the left was at the start of the year, where we had 54 unaccounted failures. So these were like the kind of failures that either crashed or like, had very it was a behavior that was not predicted previously. There were 188 passing tests out of like I think 504. And then there were 262 tests that were expected to fail. So the number of red failures were reduced to completely to 0. And then we had, I think, about 36, 35 increased tests in the X fails. That took the total number of passing tests from 188 to 276, which is just a screenshot of the latest status. So this is with ClangREPL. And then with Cling, you have about plus 10 tests. Another thing I worked on was the CI. So the CI is intended to basically ensure like testing over various settings. The nature of CppInterOp being configurable in 2 different compilers, and each of these interpreters, and each of these can be built with different Clang compilers. So you have Clang 16 all the way to 19 at this time. So at the time of the start of the project, I think just had Clang 18 added, and now we have Clang 19 builds happening. So one important part of that was the fact that small changes in the API reveal memory issues with Valgrind that were, had to be either suppressed or reported for us to fix. So the LLVM builds were cached. We worked on this with an external contributor who was very familiar with CI. So I spent a lot of time basically working with him and reviewing PRs that improved our CI infrastructure. The real big improvement is the fact that we don't regress anymore, which used to happen. We had a lot of regressions that we couldn't catch, and some of them on like Mac OS, like x86, for example, on specific Clang version. So the combinatorics of how you can regress was pretty high, and the improvements that were made to the CI basically ensures that that doesn't happen anymore. So yeah, the improvements for the regressions, like these are just some of the like specific PRs that I just had, and then specific improvements in like platform specific support. So for example, on OS X, you suffer from the libc++ and lib standard C++ conflict, and then the symbols kind of don't match up. And then there were also architecture specific bugs, which one example is like exceptions on ARM Apple Silicon, which is like a PR that we have that should be merged eventually. We have to work with someone from Apple on that. And then, yeah, finally, just a slide for other outcomes. So we had our first paper on CppInterOp, which was accepted for a poster at CHEP 2024, which outlines the backward compatible Cppyy that allows you to improve your interpreter infrastructure. There was also a lot of open source community development. We had external contributors. We had the GSOC program. We had a lot of enthusiastic participation there, and also had the chance to work with the students and mentor them, but more importantly, work with them on their projects. So there was one on CppInterOp and NumPy integration, also the interoperability with NumPy and STL containers. And then lastly, LLM and Zoe Cppyy, which was also quite interesting. And then last week, Vasil and I had a talk at a high performance Python computing event at a computing school in Aachen, like the week before PyHep Dev, where I think Jim was also there. And then the last thing is the adoption of CppInterOp in root. So that kind of comes into what next. So I'm working on PyRoot with the root team for a year. Mainly, one of the aims is to reduce the technical debt with CppInterOp and PyRoot, specifically the divergence from upstream. So this gives experiment users a lot more features with every new release of root that comes out. And it's currently 8 patches away from like a complete synchronization with upstream. This is only on the first 2 repositories, and the third one is like the cling one, and that's a little more complicated. Obviously fixing bugs and issues, which is like a routine thing, because when the users report it, we try to fix it. And then the last one is adoption of CppInterOp in root as like a novel interpreter infrastructure. This is a multi-stage process where you first land interop in root. Then we use interop's unit testing layer to plug into the Cling interpreter that already lives inside root. And then once the tests look good, you start to bootstrap parts of their like JIT call infrastructure, their dynamic library manager, and things like that. And then eventually we have like a good new addition that improves things there. So I think yeah, that's it from my presentation. Yeah, thank you.
Thank you, Aaron. Any questions for Aaron?
Just want to say thanks, Aaron. I was pushing you over the period of your internship, but I didn't realize how much work you have done. Thanks for putting that together. It was a lot of fun.
Yeah, thank you. I had a really good time working with Vasil. Yeah.
Happy to hear it was a good experience. All right, that was all we had for today. So thank you everybody for attending. Bye.
Thanks,
Thank you.
bye.
Bye.
All right.